Excellent. All right. Hi, everyone. My name is Nick Wright. I'm going to talk to you today about the dynamics of OB associations and what they can tell us about their initial conditions and their future dynamic evolution. This is work I've done with a number of people who are listed here, so I'd like to thank them all for their contributions to the various bits of work. So starting with a very quick introduction, OB associations are low-density groups of young stars originally identified because they were co-moving. They are gravitationally unbound and therefore expected to be in the process of expanding. And based upon that, people have in the past thought that they are probably have expanded in the past and therefore would be the expanded remnants of star clusters, potentially disrupted by processes such as residual gas expulsion. And the objective of the work that I'm going to present today was to go and test that idea by using kinematic data to see if we could constrain the initial conditions of OB associations. And I'm going to present results from two studies focused on the Cygnus OB2 association using pre-Gaia ground-based astrometry and on the Scorpius Centaurus association using Gaia DR1 astrometry. So Cygnus OB2, for those who don't know, is the most massive OB association known in our galaxy. It's got a total stellar mass of around about 20 to 40,000 solar masses, so comparable to some of the most massive star clusters in our galaxy, like Westland 1 and Westland 2. It's got a fully sampled mass function. There's 65 known O stars, including some with masses up to 100 solar masses. And the age is known from the low, intermediate, and high mass population to be around about 5 megayears. And for the work I'm going to present today, we're using an X-ray selected sample of low and intermediate members of the association, which has been published many times before. Now, this work started in 2014 when Richard and Parker and I looked at the structure of the SIG OB2 association, and we found two very interesting things about it that we hadn't expected. The first was that the association was highly substructured, and by that I mean it didn't have a central high-density core with a smooth radial density profile, but instead it was substructured with multiple clumps and overdensities within it. It also didn't show any evidence for mass segregation. The high-mass stars in SIG OB2 were not in any preferential location, any location, for example, where the density was higher than average. And we compared those observations with the predictions of N-body simulations and found that at about the age of SIG OB2, the only way you could explain this is if the association hadn't ever been a dense cluster in the past, but had been born with a relatively low density, a high amount of substructure, and that there hadn't been much dynamical mixing that would have erased both the substructure and led to the development of mass segregation. We wanted to go and test this idea, but this was in 2014, and Gaia was still several years away. So we went to get proper motions from wide-field imaging data. If you put together images from wide-field cameras around the world covering about a 15-year baseline, you can get proper motions down to about a sub-milliarc second per year precision. Now, obviously, that is inferior compared to today's Gaia data. It was very good at the time, and it's still quite good given that we go 5 magnitudes deeper than Gaia will go. So we've actually got proper motions here that will be better than anything Gaia can produce. This is our proper motion map of 750 members of SIG OB2, just showing their proper motions as vectors. The O stars are shown in red just to show you that they broadly follow the kinematics of the other members of the association. To assess evidence for expansion, we wanted to look at the radial component of the proper motions, which you can do by making an assumption about where the association center is and looking at the radial component of those proper motions. If the association was expanding, we would expect the majority of stars to be moving outwards from the center in some sort of Hubble flow-like pattern. Instead, what we find is there's about a 50-50 division of kinetic energy between stars moving towards the center and stars moving away, with obviously some random motion within that. And so we think that this shows a lack of a cohesive expansion pattern, and therefore that SIG OB2 is not an expanded star cluster. And this means that cluster disruption mechanisms, such as residual gas expulsion, probably haven't been at work on the large-scale dynamics of the association. When we began to look in more detail, we started to see something quite interesting in the internal kinematics of the association. And this is perhaps best shown if I color code the vectors according to this color wheel for the position angle in which they're moving. You can now begin to see that there are groups of stars all in the same area within the association that have similar kinematics relative to the association as a whole. For example, there's a group in here that's blue, green group, there's a peachy group here. This we referred to as kinematic substructure. It's sort of moving groups within the association. And these groups appear to be close to being gravitationally bound. They're relatively small, but their kinematics are consistent with being bound. And the fact that they exist 5 years after the stars probably formed tells you they can't be that far from being bound, otherwise they would have dispersed by now. So again, this tells us residual gas expulsion is probably not having an effect on the small-scale dynamics within the association. It also tells us that this association couldn't have been dynamically mixed at any point in its past. Otherwise, you'd have destroyed this substructure. Any interaction between these groups would destroy these groups, and they wouldn't survive to this current age. So again, that's putting constraints on the past dynamical history of the region and telling us, again, it probably couldn't have been a cluster. Turning now to my second target, it's the Scorpius-Centaurus OB association. It's the nearest OB association to the Sun. It's between about 100 and 150 parsecs away. It's divided into 3 subgroups, Upper Scorpius, Upper Centaurus Lupus, and Lower Centaurus Crux. And they age from about 10 megayears up to 20 megayears. The total stellar mass of the association is about 4,000 solar masses, about an order of magnitude smaller than Cygnus OB2, but a lot closer, so potentially more accessible. The sample that you see there is based upon the Hipparcos membership list from DeZeo et al. In 1999. That was revised by Rizzuto et al. In 2011, and it's their membership list we're using. The majority of these sources have vastly improved proper motions in Gaia DR1. And the reason for this is that Gaia DR1 provides proper motions that combine astrometry from Hipparcos with astrometry from Gaia's first set of observations. So you get a very long baseline and a very high precision of proper motions. So for our sample, we've got a median proper motion precision of about 0.1 milliarc seconds per year. It's about 70 meters per second. The parallaxes give us distances with a relative precision of about 10 parsecs. And there's radial velocities available for the majority of these stars in the literature to a precision of about 2 kilometers per second. So we've got 6-dimensional phase space information for a large fraction of the SCOSEN membership here. Now, because SCOSEN is so large on the sky, it's almost 80 degrees across, and because it's so nearby, you can't just plot the positions of stars on the plane of the sky and look at their proper motions. And the reason for this is something referred to as virtual expansion. If you've got a group of stars which isn't expanding, but it is in the process of moving towards you, then it will begin to occupy a larger and larger area on the sky as it gets closer. This is referred to as virtual expansion. It's one of the reasons why it's been very difficult in the past to assess the expansion of nearby associations. What you actually need is some indication of the line of sight velocity, i.e. the radial velocity. And with that, you can test Blau's linear expansion model, which is what's shown here for the 3 subgroups of SCOSEN. What's plotted on the y-axis is the observed radial velocity minus the predicted radial velocity if the association were not expanding. On the x-axis is the distance derived from the individual parallaxes. If the association was expanding, we'd expect stars on the near side to be preferentially moving towards us, and stars on the far side of the association to be preferentially moving away. So you'd expect a positive correlation between these quantities. As you can see, the data don't give us any suggestion of this. There's either no correlation or about a 1 sigma suggestion of a negative correlation, which would suggest some form of contraction. We can then look at the kinematics in 3 dimensions. This is in the galactic Cartesian system, where I'm showing for all 3 subgroups the velocity plotted against the position in each of these 3 axes. In the x and z directions, which is towards the galactic center and out of the galactic disk, you'll note that there's virtually no evidence for any sort of correlation, or if there is, there's a slight negative correlation, again suggesting contraction. But in all 3 subgroups, we find a significant 2 to 3 sigma significance evidence for expansion, i.e. a correlation between these 2 quantities. Now, we looked back in the literature and found this had actually been seen once before in a moving group, which found exactly this same trend. No expansion in x and z, and significant expansion in y. What we think is happening here is instead of there being a global radial expansion pattern, which might be predicted by things like residual gas expulsion, instead there's potentially some sort of tidal heating or tidal stripping acting in the direction of galactic rotation. That's just an idea at the moment. It's something we're looking into investigating. I'd be happy to discuss that with anyone. And finally, you can perform some sort of correction for the virtual expansion based upon the node and radial velocities of these subgroups. And that allows you to make a correction that gives you a qualitative picture, not a quantitative one, but a qualitative picture for the kinematics in each of the subgroups. And again, I'm color-coding the vectors here by their position angle. What I want you to take from this is basically there is no clear radial expansion pattern within the subgroups. And instead, there is hints again of the kinematic substructure that we saw in Cygnus OB2. It's a little weaker, but I think there's hints of it there. So my conclusions, OB associations have long been thought to be the expanded remnants of star clusters. And what we're finding is that while OB associations are expanding, they are gravitationally unbound, and so they will expand. They're not expanding from any compact set of initial conditions, but rather from an extended and highly substructured distribution. There's a number of implications for this. It means that all those high-mass stars in Cygnus OB2 didn't form in any particularly dense or massive cluster, and that's important for models of high-mass star formation. It tells us that residual gas expulsion is not having a significant effect on the dynamics, both on the large or the small scale of these systems, so that's important for models of feedback. It tells us that any planetary or binary systems that we find in these associations may never have been in any particularly dense cluster. They might have been, but we can't say that for sure at this point. And so that's going to be important when we compare the properties of binary and planetary systems in associations versus those found in clusters. And finally, I think it's quite important that there isn't any comparison made between individual star clusters and individual associations, because they're not in the same evolutionary scheme. A better thing to do would be to compare associations with large star-forming complexes, such as the Orion complex that I think we're going to hear about next. And I think that's a more reasonable comparison and a more likely set of initial conditions for the associations that we see. So thank you very much.
Thank you very much. Questions?
Jackie Faraday, American Museum of Natural History. I was wondering if you've looked at the mass distribution or the temperature, whatever you're going to do to get to the mass, to see if there's any correlations with the kinds of objects in there and those beautiful distributions you see.
We haven't done that in a huge amount of detail. In SCO-SEN, we're mostly picking up OB and A-type stars, so we've not got a huge sample with which to perform that correlation. In Cygnus OB2, the O stars are shown here in red. They broadly follow the distribution of the stars that are of lower mass. We go down to about 0.3, 0.4 solar masses in this sample, and we can't find any clear indication of a difference as a function of stellar mass. But because there's so many other things going on, it's not immediately obvious to us what the right thing to test would be. Any suggestions? More than welcome.
Hi, I'm Lauren Matilsky from University of Colorado Boulder. I'm wondering about the dynamics of these OB associations, and in particular, is the data from Gaia good enough to actually measure the 3D accelerations of these individual stars? And like, if they're not expanding now, are they slowing down? Are they starting to expand, or are they basically in a situation of equilibrium?
I don't think we could track expansion as a function of time, simply because we've only got measurements of velocities now. We need to make perhaps some assumption about past configuration. We can obviously model the expansion of these systems in the galactic potential, but that's not really, I think, questioning any sort of model. That's just making a prediction. Was there a second part to your question that I missed? Sorry.
Hi, I'm Doug Guys, Georgia State University in Atlanta, and just curious about numbers of runaway stars in these two environments. Maybe those were excluded from your samples, but do you have any sense about what sort of fraction of runaways you're finding?
We specifically excluded anything that was more than 3 sigma from the standard deviation in Cygnus OB2, partly because we're looking at the center, and so we expected them to be probably contaminants. In SCO-SEN, we looked at everything, but there wasn't any immediately obvious contaminants within the area of SCO-SEN. And I think there's a bias there in the fact that because we're looking in a limited spatial area, anything that has been kicked out is potentially out of our field of view. There are definitely candidate runaways from SCO-SEN and from Cygnus OB2 of various masses. I don't think the census is complete yet, which is what you'd want, I think, to start to understand the problem.
Scott Wolk, CFA. So could you possibly be looking down the barrel of a filament here instead of more of a spherical structure, and could that count for some of the differential motion you're seeing that's overlaying each other?
I think partly, and I think we are seeing hints of that in the parallaxes for these objects. my previous assumption was that you want to make an estimate of the line of sight spatial distribution. You go with the plane of the sky spatial distribution. But certainly, the kinematic subgroups can't be at the same distance of each other, within a few parsecs, because they're just going to be interacting. So I expect there's going to be a few or 5 or 10 parsecs separation for them to survive. But this is only showing the middle of the association. It's about 30 parsecs across. So if those groups are 10 parsecs separated along the line of sight, then I think they probably would survive, at least up till this point.
Hi, Kim Ward-Duong, Amherst College. These are absolutely lovely results, and I was wondering about the sort of loose associations that you see are very kind of loosely bound to each other, and if you could speak to how we might expect the multiplicity properties of these stars to evolve in time if we were to compare against older field populations.
By loose associations, do you mean moving groups or the other OB association populations?
Oh, sorry, within SCOSEN, the kind of loosely bound, sort of nearly dispersing groups.
Okay. We didn't have high enough sample size to look at the substructures in SCOSEN, but in SIG-OB2, these sort of subgroups here, their kinematics are consistent with being bound. We can't say any more because we're kind of at the limit of our proper motion precision, and annoyingly, a lot of these objects are too faint for Gaia to detect, so we've got to just build up our baseline of ground-based data, really, and see if we can get better. There are studies of the high-mass binary population in SIG-OB2 that have shown there is a higher, well, get my wording right for this, there are more wide binaries in SIG-OB2 amongst the high-mass stars than you find in other clusters and other similar associations, suggesting potentially that the fact that it's never been through a high-density phase has allowed those systems to survive. I think Doug might be in a better position to answer this, because I think it's one of his ex-students that's done some of the work on this.
Okay, let's thank the speaker again. We move to next speaker, who is Marina Konkel from the